We're from Intel and mostly working on the hardware feature enabling in the virtualization, KVM, QEMU, and other VMM. So yeah, today we want to share our work on the to optimize the VM performance on the Intel Hybrid CPU platform. So it's a client CPU. So yeah, I think people might be curious why virtualization on client is making sense. So I think in recent years we have seen a lot of cases, and also other customers want to like to use the client system to run the VM workload. So that's why we are trying to see how we can optimize this on the because Intel from I think 2 years ago from Alderlake, all the client CPU is hybrid. So yeah, let's get started.
Okay, thank you. Our talk will cover these three parts. First, let's have a look at Intel's hybrid platforms and have a look at its hybrid topology. And then we will introduce our hybrid CPU topology proposal in QEMU. And then Zhenyu and I will introduce our scheduling solutions in guest for Windows guest and for Linux guest. Okay, Intel introduced the hybrid CPU architecture from the Alderlake, and this is an example of Media Lake. We can see that there are two dies, the compute die and the SoC die. The die is hybrid, and in the compute die, the module is also hybrid because there are two types of modules. One module contains the core. The core named it means P-core. And another module. Okay. Another module type contains 4 atoms. Atom is the E-core. So the module is hybrid. And the core is hybrid too. Yeah, there's a core P-core and the atom E-core. And there's atoms in SoC die. This is a low power E-core. Although the atoms in SoC die and in the compute die, they have the same macro architecture, but they have different frequencies. And the thread level, thread is also hybrid because the P-core has 2 threads and the E-core has only single thread. And for the cache topology is a hybrid too. The P-core's module, in the P-core's module, there's one L2 cache. This means one P-core will has its own L2. But for the E-core, the 4 E-cores shares one L2 in the SoC die, in the compute die. And on the SoC die, 2 atoms shares one L2. And L3 is also hybrid because the compute die has a L3, but SoC die doesn't. The L3 is the only way to identify the items, whether on the SoC die or on the compute die. So there's maybe a question, why does guest need to care about hybrid CPU? Yeah, we test the single core performance in the guest by running the vCPU thread on the different cores. We can see that there are 4 atoms, single core atoms. And on each 4 atoms, the P-core could have the better performance, but the low power E-core has the worst performance. So the performance is the most important reason for us to enable the hybrid CPU for guest. And another reason, because some guest OS has a special optimizations for hybrid CPU. For example, Windows 11, it optimizes its scheduler based on Intel Thread Director feature. And another reason is the feature. For example, the hybrid PMU. The PMU on the hybrid client form, hybrid client platform. Yeah, different cores have the different PMU events. And currently, our hybrid CPU solutions are mainly used for the gaming case because the game requires better performance, but the client is a resource-limited platform, so any improvement is very important. And there's another hot topic about vCPU pin. We believe that pin vCPU is a precondition of hybrid CPUs in guest. If we don't pin the vCPU on hybrid client, then the vCPU may migrate to different cores. Then the hybrid information in guest and in host will not match. This will hurt the performance. And there's the double scheduling issue. Double scheduling is not a client-specific issue. The cloud keys also has this issue, but since the client is resource limited, this will hurt the performance significantly. This means there's two schedulers. One is in guest and one is in host. If we don't pin the vCPUs on host, then both two schedulers could work, and concurrent scheduling results in more task migrations and context switch. So the hybrid CPU information is important. How to configure it to the guest? We have the proposal. Currently, the QEMU configures the topology by SMP command. With the SMP, then QEMU creates a CPU or cores object. For x86, there's a special array named possible CPUs. Each element in possible CPUs is mapped to a CPU object. And for the PPC, the element of possible CPUs is mapped to the core object, and the CPU object is created in place under the parent core. But this is not enough. We can rethink the Alderlake example. All the CPU topology level may be hybrid. The hybrid die, hybrid module, hybrid core, hybrid thread. So if user want to configure the hybrid topology, then we need more topology devices. So this is our first step to the hybrid topology. We need to abstract each CPU topology level as a device. We already has these three devices: CPU device, core device, and the cluster device. But to complete the topology tree, we need more. For x86, we need the socket device, die device, module, core, and thread. Then how to connect the different devices? In our RFC, we introduced a virtual CPU bus. Currently, the bus structure in QEMU could manage the topology very well. It is used in the CXL and PCI to manage the device topology. So I think it's very natural to also use bus to manage the topology relationship. Then with such device, we could allow the user to build the device tree through the command line. This is our hybrid CPU topology proposal. Yeah, allow the user to custom their own device tree. For example, this socket 0 could be created by the device command. Yeah, device command creates a CPU socket, and the ID is socket 0. And then the die 0 and the module 0, module 1, and the P core and the E core. And at last, the user could connect the threads to the P core and the E core. And there's additional benefits. With so many topology devices, then we could reflect the topology relationship in the QOM path. Now, we could reparent the child device to the proper parent device, and we eventually will have the QOM path to reflect the topology relationship. And maybe we could support other level hot plug, for example, the socket level hot plug, because now we have the socket device. And for x86, it could help to emulate the features which has a topology dependency. Currently, QEMU supports the running average power limit, this ripple feature. This feature has registers, which is a package or die scoop. When we have the socket and the die device, then we can save and load the registers in such device, and all the topology child could share the same register value. There's our idea. We also want to go further to support the hybrid cache topology. This means we also want to abstract cache to device 2. For example, there's a L3 cache, we could create by the command line and specify its parent as a die 0. So all the child device under the die 0 will share the same as L3. We have posted our V2 RFC to the mail list. Yeah, it's a very huge work. Welcome your feedback and comments. And then Zhenyu and I will introduce our scheduling solutions for the hybrid guest.
Yeah, so besides the hybrid topology issue that we have to resolve, right, how to define that for the guest, and then we actually have other scheduling optimization. So because hardware not just provide hybrid topology info, but it has other features that can provide some performance and energy capability of the CPU at runtime and to help the OS scheduler. So this is Intel calls this the first version is the hardware feedback interface, and the second version is the Intel thread director. It basically provides a table in the memory that can you can see that each logical processor will have a line of definition of the performance and the energy efficiency. So in initial version, it only support one class. So you can check the change on the hardware, and the second version ITD has added the classification support, which means that it can track the instructions that the application running on the CPU, and it analyzes what's the class based on the instruction, IPC based, and it will provide you a class. So this class you can reference this as the indicator from the hardware that which is the best column you can search to what's the indicator you want to use. So if you want to use if OS scheduler want to more performance schedule, so it will check the performance columns, and it can compare the ratio, right, between different processors. Or if you want to currently want to more energy, and you can compare the energy column. So that's the basic idea. And hardware will also can be notified the OS scheduler through the thermal interrupt. So any change in this table from the hardware will be notified to the OS scheduler. So yeah, we know that this hardware feature, has been enabled in the Windows guest. So we want to see what's the benefit, right? What does it really help? So we do this a lot of combination testing, right? The baseline is the without hybrid topology, but only have SMP topology, and we also add several options like enable the ITD virtualization or setting the CPU affinity. So from our conclusion, this is a 3D mark in Windows 11. And we can see that all those things combined has reached the best result for us. So with the hybrid, the result is that we need to combine these three elements to get the best result. So this page is how we currently do the ITD virtualization. So I think it's very straightforward. So we try to emulate several ITD related MSRs. So how to set up the table for the guest. And we have a KVM is talking with the Linux host HFI and the ITD driver, which basically set up the table in the kernel, and the KVM can get the information from the driver and provide a virtual table for the guest configuration. So yeah, that's basically the idea. Yeah, but we know that even with this might not be enough for the Windows, right? So we have several dependency. One is I mentioned that we need interrupt support, which is thermal interrupters. We have to add the thermal interrupt injection in the KVM. And also we have other maybe unknown onshore dependency, but we add that anyway, like the ACP, ICP, PC table. So Windows guys just told us it might be required, so we just added that. And also we future, so we like to move this dependency in the user space based on the recent QEMU user space MSR handling framework. So yeah. This is our, we actually send the patches to upstream, so I'll got some comments. Yeah. Okay.
Okay, the last part is about the Linux guest, how to optimize the scheduling in Linux guest. Linux guest use ITMT scheduling. ITMT is Intel Turbo Boost Max technology. This means some CPU cores can reach higher turbo boost frequencies, and thus these cores have better performance. And ITMT scheduling detects cores with the highest available turbo frequencies and prefers those cores to place tasks. On the hybrid platform, ITMT scheduling implements priority order as the first P call, then E call, then low power E call. Low power E call means the atom on the SOC die. And at last, it can consider the P calls SMT thread. There are two keys. For new created task, scheduler will first consider to place it as the free P call, then free E call, then free low power E call. And at last, scheduler could place a task to the P calls SMT. And there's a same logic at the idle load balance case. The scheduler could consider to pull the extra task from the basic call to the free call. It first considers the P call, then free E call, then free low power E call, at last the P calls SMT thread. So for the SMT scheduling, there are four cases based on two conditions. That's whether to enable ITMT in guest, whether to ping vCPUs at host. Of course, there's the worst case. This is the right case. This means we enable ITMT in guest, but we didn't ping the vCPU on host. Then the guest and host both have the hybrid knowledge, but since we didn't ping the vCPU, then the vCPU thread could migrate to different cores, and the guest will have the wrong information. This will hurt the performance. So we can compare the other three cases. The first, this is the case that we ping the vCPU at host, but we compare the guest with or without ITMT. Look at the left picture. We run the single core benchmark in guest for 10 times. And for the guest with ITMT scheduling, the result is very stable. And compared with the right picture, we can know that all the single thread running at the P-core. But for the guest without ITMT scheduling, the result is random, and the task may run at the low power core or E-core or P-core, so the performance is unstable. So now we have the conclusion. If we ping the vCPU as a host, then it's better to enable the ITMT tool in the guest to have the best single core performance. And then we can compare that case that for the guest, the first case, we ping the vCPU at host and enable the ITMT in the guest. Then, since the vCPU is pinged, the host's scheduler won't work, but the guest has ITMT scheduling. Its scheduler has hybrid knowledge. And another case, we didn't ping the vCPU at host, and we also didn't enable the ITMT in guest. Then, since the ITMT scheduling is enabled on host by default, so the host scheduler has a responsibility to optimize the hybrid scheduling by schedule the vCPU thread. We use a Hackbench to compare these two cases. We can see on Hackbench, the guest with ITMT, also with ping vCPU, it can achieve the 8% improvement. This is mainly because the vCPU is pinged. Since a vCPU ping could reduce double scheduling overhead, it can significantly reduce context switch and CPU migration on host. So we have the conclusion for the Linux guest. The best option to get the best performance, we need to ping the vCPU first and enable the ITMT scheduling in guest. Currently, this work is under the POC state. We implement virtual MSRs to give guest a highest performance hint. And then guest can cite the ITMT CPU priority based on the hint. But we also want to use the PVSCAD framework, which is proposed by Google in QEMU mail list. This framework is a more general way to improve guest and host scheduling. And we can apply ITMT to this framework. And at last, I also want to thank my other colleagues. They helped us to bring this topic to here. Yeah, thank you. Do you have any questions?
Okay. Yeah. What do you think are the main uses for virtualization on client platforms? Because that may choose whether you pin or whether you don't pin.
Yeah. So our current customer usage is we mentioned like the gaming. So they basically want to use the consumer setup and to run the remote gaming for the client.
So sorry, what I meant is like gaming in the sense that you run full Windows VM all the time, or gaming in the sense that you start the VM just to play the game.
Windows VM.
Yes, but do you use then Windows almost all the time, or only to play the game and then you turn it off? Because I guess games you can only just pin them to P cores and ignore that E cores and low power E cores exist completely.
Okay, yeah. So Actually, on system, you have a multiple CPUs. You can have a different setup, right? So you don't have to use all the CPUs, but you can use part of that. That's okay. Depends on their VM configuration. So maybe they can run 2 or more. So yeah, that's okay.
And is there also used for developers? Like maybe developers may be okay with the e-course, but gaming, yeah.
Right. So we have other cases like education. So they want to provide education setup based on the VM, so that will be easier to manage and deploy to the students. So yeah.
So for education, you would also use the e-course.
Yeah, use the e-course as well.
Thank you.
So I think when we post these patches to the upstream, and we got comments to work on the hybrid topology first. So if you have any more comments about QEMU topology, welcome to discuss with us. So yeah, thank you.
Thank you all.